Hello, my name is Brian. I'm a part of Team Juno with Wenjay, Danush, and Tristan, as well as our advisor, Professor Mohammed El-Hadedy. I will present an overview of our reconfigurable S-curve motion controller system, as well as the progress we have made on it. As seen in the video, S-curve motion profiling is a powerful tool to significantly improve payload stability and smoothness of transportation. The base idea is that the corners of the traditional trapezoidal profile are flattened out into the S-curve profile, hence its name, where each order is a varying level of smoothness of the said S. This profile is what we'll map for our motor outputs to the various devices we will showcase in this presentation. There is previous work done by a predecessor group that implemented the first order S-curve and trapezoidal equations in Verilog on a Pink C2 FPGA board. Our design has changed to be more of a software-based implementation, but it's cool to point out that there are many approaches to enabling more motorized S-curve motion profiles. Here's a video of the previous group's implementation of the S-curve motion profile. We'll start out with the simplest implementation of straightforward and back motions. Our main targets will be stepper and DC motors driving a payload with our algorithm. Each motor has their own specific properties that apply them to various different applications, but our goal is to show that our algorithm will work regardless of that platform. This is the first step to proving that our system is truly reconfigurable and will be adopted and accepted as a trademark one-for-all system to use on any kind of motor driver device. Here are the results from our open loop implementation with inputs of distance equals 6 centimeters, total time is 10 seconds, and order equals 4. Here is a demonstration of our free run movement. In practical applications such as remote deployments and search and rescue missions, there is increased demand for unmanned ground vehicles, which is why we've decided to take some of the previous analysis and implement our own RC DC car vehicle as seen in the image on the side. For our UGV testing demonstration, we are able to host a remote web server that is able to send our S-curve motion profiles commands to our implemented RC car and have the accelerometer return the data readings back to the host. For our final test application, we decided to test just how far we can push our system and decided to build our own custom drones to be integrated with our code. Due to the nature of most commercial drones being closed source for their flight software, we decided to build two separate drones, one with a Pixhawk 2.4.8 and a Navo 2, the most common upon our research flight controllers that we could find. Both are supported by a companion computer Raspberry Pi to generate our code and drive the drones through the DroneKit API. We're in the process of testing and calibrating all of the hardware and sensors on the drone, but we're hopeful that with our working code that compiles and runs, that we'll be able to fly a drone completely and automatically just with S-curve motion profiling.
Introduce yourself, please.
Hello, my name is Brian Banta, and I'm part of Team Juno, and we're testing our drone calibration to see if our motors are working correctly and see if any fail for any roll pitch yaw movements on our setup.
Sure. And I'm Professor Muhammad. Muhammad Ali. I'm the mentor of the Geno team, and we are now starting the test. Go ahead, Brian. the calibration have been done in the audio pilot and the mission planner. And thank you, we appreciate it.
Thank you.
Hi, this is Professor Muhammad Ali, the mentor and the head of the team Geno for the NASA Mines, and this is actually test number 1 for the drones using Naviu 2 as a flight controller. We try to do our best on fixing the whole entire drone with a lot of technical issues, and even due to the COVID-19 and all these problems we faced and the technical problem, but still we build the drone. And the previous video even show how the PixHawk work, and we are in the process of loading the motion control we developed as a team on the drone using Naviu and the PixHawk. So what I have here is on my Linux machine, I set up the Q ground control while using the wire communication IP. I define the Naviu on the board on the networking with the Q ground control, and I just arm it and is ready to use a radio controller for doing the test. So test should start now. First of all, we're gonna push arm and completely full on the arm while the GPS is determining that I'm sitting now in the office. Then the controller will start doing the work. Going up and down, changing the communication after we calibrated the drone, and everything works perfectly as we expected. And thanks a lot, and talk later about the next step for the other parts of the project. Thank you.
Thank you for listening to our presentation, and we look forward to hearing any feedback or questions about our project.